This is HRW98P0105. A machine pulls a 46 kilogram trunk 1.9 meters up along a 40-degree ramp at a constant velocity. Its force on the trunk is directed parallel to the ramp. The coefficient of kinetic friction between the trunk and the ramp is 0.40. They want to know what is the work done on the trunk by the machine's force, and what is the increase in thermal energy of the truck and the ramp. Okay. First off, I need a force, because to get the work done, I'm going to have to do force times distance. So I got to figure out what this force is that's pulling the trunk up the ramp. So let's do a free body diagram. You guys probably thought you were done with those, huh? Never! Okay. Sorry. Okie dokie. So we've got, here's my mass. Go 40-degree ramp. Oh, I can't tip my paper to do a proper... Oh, this is very sloppy. Lo siento. Okay. So I've got a mass of... What is that? 46 kilograms for my problem. What forces do we have here? Well, I've got... it pulls something up the ramp. So I've got a force up the ramp. I don't know what it is, though. I'm just going to call it F. Boom. Okay. Well, if there's friction, and this thing is being pulled up the ramp, and it is moving up the ramp, that means I must have friction the other way. Don't know what it is, but I know it's there. I've always got gravity. Okay. In this case, gravity is always mass times gravity, mg. Just leave it like that. And I know this angle is 40 degrees. Okay, and finally we have the normal force. Okay. Okay, now there's a big fat clue here. It says it's being pulled along this ramp at a constant velocity. That means the net force has to be 0. Okay. So, I need to know what F is. Well, to know what F is, I'm also going to know what friction is. To know what friction is, I'm going to need to know what normal force is. And to find normal force, I'm going to have to do the Newton's second law in the y direction. So, I'm going to go ahead and just randomly assign. I'm going to say up the ramp is plus x, down the ramp is negative x. This is going to be plus y. Come on, y. And negative y. Okie dokie. So, well... in the y direction, I've got F net in the y direction equals, well, I know it equals 0, so I'm just going to put that 0. Well, F net in the y direction, I've got N pointing up, normal force pointing up, minus. Pointing down, neither of these point down at all. And the force of gravity points in the y direction a little bit, but not all of it. So we have to find Fg in the y direction. Well, if you look, that is the side of a triangle. I've got a triangle, it's kind of like where the hypotenuse is mg, and the side I want is adjacent to the angle. So I'm going to use a cosine here. That is going to be Fg cosine of the angle. Okay, so over here I've got normal force minus Fg is mg. I'm going to go ahead and put that in there. mg cosine theta equals 0. Well, that means that the normal force equals mg cosine theta. Boom. Okay. I could get a number for that, but I'm going to leave that for now so that I don't get calculator errors and rounding errors and stuff. Okay. Well, that's good to know, because when I do this in the x direction, and I think I will, how about purple, and I'm going to go ahead and make this full screen. Okay. In the y direction, I'm sorry, x direction, okay, I know it is also going to equal 0. Well, in the x direction, I've got F is straight up on x, positive x, so I've got F. That's the only thing that points up the ramp, so that's my only positive thing. But down the ramp I've got, so minus, I've got friction. I also have the component of gravity that is in the x direction, so that's F oh, come on, FGX. Okay, so I'm gonna subtract that, FGX, that all equals 0. Well, force minus friction is mu times the normal force. And then the x component of gravity, well, that is across the way from the angle, so that's going to use a sine. So it's going to be mg sine theta equals 0. If I solve for f, I get f equals mu times normal force plus mg sine theta. Okay. Now, we said normal force is mg cosine theta. So really, the force is mu mg cosine theta plus mg sine theta. Okay, so at this point, I'm going to go ahead and put numbers in, and I'm using all of mine. I think for me, mu was, let me just go look, 0.4. Looks like it's that way for everybody. Go ahead and write that in. I also have, well, I've already got m written down. G I'm going to need. The angle I have written down. So I've got everything I need. I'm going to go ahead and put numbers in and get, and get what the force is. Oh, not that. There we go. Okay, so put that all in a calculator, blah, 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 blah. And then I get 427.9 newtons. Okay, then, so the work done is going to be force times the distance it was dragged. And I don't have any angle here because the force is parallel to the ramp, and the problem says machine pulls, the force on the trunk is directed parallel to the ramp. So they are in the same direction. I just get to plug them in. My D is 1.9, so 427.9 times 1.9 gives me 813.01 stuff, say 13 joules. Take a look. Yes, that is the answer. Okay. Now, part B is where some people were having a lot of trouble. What is the increase in thermal energy of the trunk and the ramp? There's two ways we could get this. Number one is a good clue whenever they talk about thermal energy, right here, they're really talking about the energy lost due to friction. So the energy lost due to friction, we could say, is the work done by friction, which would be a negative number because this was dragged up the slope, friction is down the slope. So we could find it that way. I'm going to go ahead and find it that way, and then we'll find it a second way and show that they're the same number. So the work done by friction is going to be negative friction, force times distance, where the force is friction. I'm doing negative because, again, friction is down the slope. I'm sorry, yeah, friction is down the slope, but the thing moved up the slope, so F and D are anti-parallel. Okay, we already found friction. Friction is mu mg cosine theta. Mu mg cosine theta. And then D was 1.9. If you put all that in the calculator, you get 262. Rounds to 262. Okay. Notice that is the correct answer. But there's another way to get it. Another way to get it is to realize that when you drag this thing up your ramp, it gains height because this is 40 degrees. It is dragged a distance of 1.9 meters. Therefore, it gains a height of sine 40 times 1.9, or in this case, 1.22 meters. So this is 1.22 meters. Well, if it gains height, it gained potential energy. So the change in its potential energy was mg times the change in height. In this case, if you do all of that, you get, well, let's see, 46 times 9.8 times 1.2 gives me 551. Yep, if you round it up. This is actually 550.56, but going for this. Well, here's the thing. If the force did 813 joules of work on the thing, that means that the force put 813 joules into the block. But the block's potential energy only increased 551 joules. So that's not all of it. Where did the, hang on, orange. Where did the, let's see, it put in 813 joules, but I can only account for 551 of them. I mean, the rest of it, it's not a change in kinetic energy because it was dragged at a constant velocity. So where did the extra, put this in a calculator, 262 joules go? Well, it got dissipated as thermal energy. Basically, it got turned into heat. And so that was the increase in thermal energy. See? Same number. It's kind of creepy, huh?